Kinetic energy. It's the first type of energy that we'll discuss. And all we're going to do today is get our heads around what it means, what it sort of stands for, and how we can describe it mathematically. Which I guess is everything there is to know about kinetic energy. So, let's just start with a little scenario. I'll draw a little car here. There it goes. And if we have a car that's initially standing still, not moving at all, it would have no kinetic energy. Remember, kinetic energy is energy that's due to motion, right? Or more specifically, velocity. If you have speed or velocity, then you have kinetic energy. So if we apply force to this car through the wheels and the union, we can cause the car to accelerate, F equals ma. And the car will then change its speed to something more. So let's put the car over here later. And now the car will be going, say, 5 meters per second. And to do that, we had to apply force, which causes an acceleration or a change in speed. And obviously the car had to move a certain distance or displacement, d. So you can see how work is being done here because we have a force and a displacement. And that's what work is. It's force times displacement. So if we write that down, the work would be F applied times the d. And don't forget that what we're doing is we're actually giving the car energy. So we're changing it from zero kinetic energy to a certain amount of kinetic energy. And work is also defined to be the change in energy. So let's look at this equation. And let's just kind of mess with it a bit. F applied, force equals ma, right? Because that's Newton's second law. So I can replace force with ma and get this little equation. At the same time, I can also describe this situation using a kinematic equation that looks like this. There's a d and two different speeds and obviously an acceleration. And if I just move the v1 to the other side, the v1 squared, I get this. And then if I divide both sides by 2, I get this. Oops, equals AD. So all I did is mess around with it a bit. It didn't really change anything. But AD is the same as this AD over here. So I can use this part as a substitution. So when I substitute this for that, this becomes work equals m multiplied by a half times v2 squared minus v1 squared. But remember, we said that v1 was 0. So that really becomes, I'll put the half out in front, and then the m, and then v2 squared. But v2 is really just the speed that the car would be going. So we don't need to call it v2 anymore, and we don't need to call it work. We could call it kinetic energy, because work and energy are the same thing. And it would be 1/2 mv squared. So the kinetic energy of an object is easy to calculate. You just need to know the mass, and you multiply it by whatever speed it's going squared. And the direction doesn't really matter because it's an energy, so it's not a vector, it's a scalar number. So what you could say is you could say that for our little car, now it's going 5, it has that much kinetic energy. We can figure it out. Let's do it. Let's see how much kinetic energy our little car has. Now we have to give it a mass. So let's pretend that our car has a mass of 1,000 kilograms, just to make the math easy. Right? So then you go down to your little equation, and if you wanted to figure out how much kinetic energy a car had that was 1,000 kilograms and it was moving at 5 meters per second, you would put in 5 for the speed, and you would get 25,000 divided by 2, which is 12,500 100, I believe, joules of kinetic energy. So it's pretty easy. It's almost like a plug it in and play. Now you could also express that. You'd get the same answer here. You could also call it the work that was done to the car in getting it from 0 to 5 meters per second. It's the same number, same thing. So whether you call it the work done on the car or the kinetic energy, it's still the same amount of energy. So there's our first equation right here that we'll use for kinetic energy. But what happens if the object doesn't start at 0? What if we want to increase the speed of an object? So let's now imagine a car is moving at 5 meters per second. Nope, not squared, sorry, just 5 meters per second. How much work would need to be done on the car to bring it to 10 meters per second? Keep putting that little square in there. No, 10 meters per second. So let's say we wanted to speed it up. Now it's not starting at 0. Well, we could do this a couple of ways, and the simplest way to do it is to set this up with an equation that we're probably going to start using a lot, this format. We're going to say that work is equal to force times distance, right? It's also equal to 1/2 mv squared if it's kinetic energy. But you can easily say that work is equal to any change in energy. If you change the energy of anything, it'll be work that's done. And in this case, we're talking about changing kinetic energy, so I'm going to put a little k beside there to remind us. And the delta sign in math can be translated to mean ek2 take away ek1. Which means that if we take the kinetic energy at the second speed, which would be 1/2 mv2 squared, and we subtract the kinetic energy at the first speed, 1/2 mv1 squared, we will find out the difference in those two energies. And that difference of energy is how much work would have to be done. We can simplify this mathematically a little bit if we pull out 1/2 m as a common factor. Then we get this, which makes the substitutions a little bit easier. So let's figure it out. The answer would be the work would be 1/2. On our car, it's 1,000 kilograms, and we wanted to go from 5 up to 10. So 10 is the second speed, 5 is the first speed. Remember, it's always 2 minus 1. And it's not 10 take away 5 and then squared, which would be 25. It's 10 squared take away 5 squared. So that's 100 minus 25. So it's 75, right? So if I swing up here, the work would be half of 1,000 is 500, and 100 take away 25 is 75. And so if you multiply that by 500, 7 5s and 35, is that 37,500 joules of energy. That would be the extra energy you have to add to the car in order to get it from 5 meters per second up to 10 meters per second. That's not the actual total energy it now has, it's just the amount we've added. So see, it started off at 5, and when it was moving at 5, it already had this much kinetic energy. Now to go from 5 to 10, we've seen we have to add this much energy or do this much work to it. So the final little question we might want to find out is, how much kinetic energy does it now have? Well, it started off with, if we go back to our numbers, started off with 0, and we added 12,500 to get it to 5 meters per second. So what we could do is just start with 12,500. And then we said we would have to add an additional 37,500. So we could add that. And then the total amount of kinetic energy that it would have should be 0, 0, 0, 0. Looks like it should be 50,000 joules, right? Makes sense. And we can also do it this way. We could also just figure out the kinetic energy for any object with a mass of 1,000, right, times the speed it's going, times 10 squared. That's, I didn't write it, but I'm using the first formula that we talked about, like that, right here. And that would be half of 1,000, which is 500, times 100. Then it would come out to the same amount, 50,000 joules. And that's really all there is to kinetic energy. Calculating how much kinetic energy something has with the speed, or calculating how its energy might change if its speed changes. Now there is one interesting thing that we should just point out before we quit, and that is what happens if you slow down. Let's do the very same car, but let's change this. Let's say that it starts off at 10 meters per second and it slows down to 5 meters per second. And if that were the case, we have the very same thing that we had before. Work is the change in energy. Work would be the EK 2 take away EK 1, and it worked out to 1/2 of M. I'll shortcut this here. You can check up above if you're not sure how I got this, but it's the same thing. And the only difference would be 1/2, 1,000. Right in here, V2 would be 5 squared, and V1 would be 10 squared, which means this is going to work out to a negative number, right? And since it's all the same numbers, it's going to be negative 75 instead of positive 75. So going back up here, we got an answer of 37,500. We're going to get that same answer here, 37,500. But because this is going to give us negative 75, the answer will be negative. So we have to find out what that means. And we just finished talking about the fact that energy is a scalar and direction doesn't matter. So plus and minus do not mean direction. We have to figure out what plus and minus might mean in the case of energy. And if you think about it, it's pretty obvious. In the first case, we sped up the car, so we added energy to it. Positive answer. In this case, we slowed down the car, which means we had to take energy away from it, right? The way you slow down a car is by taking energy away. The way you take energy away is through the brakes. The brakes squeeze on the wheels and create a lot of heat. So what happens is you take energy away from the moving car by turning it into heat, and the car slows down. So it's an energy transformation. So what we have to remember is that a positive number means that we are gaining energy, and a negative number means losing energy, a gain or a loss, not necessarily direction. For kinetic energy, slowing down means you would lose energy, and speeding up means you would gain energy. So that's where you might get some negative and positive answers. And that's really all there is to say about kinetic energy for today.